relational data model. Before there were computers, before there were even databases, folks were trying to think on how is it that we would store data and how we would retrieve it and query it, and a lot of research went into what is the formality of representing data and the various operations that we might want to be able to do on the data. And just like we did, there was a lot of mathematics behind procedural and functional programming before there were computers, right? Lambda calculus and all the formalities of way back when there were no computers, and we were trying to invent the field. Same thing for databases, right? We were trying to come up with a formality on what is it that we can do. How can we query it? A set of operations that are now referred to as a relational algebra was designed, was created to formally represent or be able to calculate and execute various operations that you could do on a database. Here are some of the operators that allow us to operate on a data set. Presumably, data sets are tuples that have multiple, single entities that might have multiple attributes. Presumably, organized into classes or types of entities, of which one, if you belong to a particular entity, you have the same properties as other instances of the same entity, right? So if you are an employee, then you share the same characteristics as other employees, right? You all have a first name, you all have a last name, probably you all have this usernames, passwords, salaries, the date that you were started working here. So we all share the same type of properties, and we all belong to a data set of employees. And there might be other data sets that describe other phenomena. There might be other data sets for the departments in a company. There might be data sets for companies in general. And somehow these data sets might be related to one another, such that certain employees might work in a particular department and other employees might work in a completely different department. So these data sets are related to one another. And we would like to be able to describe what are the operators that we can apply to all these types of data sets, right? So you have, based on a lot of the set theory, this is a subset of the types of operations that we would like to be able to do. So these are somewhat abstractions on top of set theory that are very useful for our particular application. So let's look at a couple of operators. First, let's look at the select operator that allows us to retrieve certain rows, right? So you have an entire data set of maybe of all employees, of which you're not interested in all employees. You might be interested in a subset of employees that meet a certain criteria, right? So you might be, it says, don't give me all three. I'm not interested in all 10,000 employees. It might be a subset of the ones that are in a particular department or that make a particular salary range, right? So given a particular criteria or particular predicate, right, I might filter that large set into a subset. Okay, so select allows me that operation, right, to filter a large data set into a subset of that larger set. It returns all the attributes, all the columns, but of some rows. Okay. Whereas project, just like select allows us to filter, perhaps vertically. If you think a data set might be organized into vertically, right? And select allows you to filter and only get a certain subset of those data points. Project allows us to filter horizontally, right? Where you might not want all the properties, right? You don't care about my password. Maybe you shouldn't care about my password. So maybe I don't want to share my password if in that query, in that data set, right? So I might not provide that information as part of my query of the data points that return in the select. I might only provide you maybe with a user ID, or maybe a username, or maybe the email, or maybe if it's personal information, then you might want my first name, my last name, my address, right, my phone number. But I shouldn't share with you maybe my salary, right, or my date of birth. So certain things might be private. So project allows you to filter horizontally. What are the fields that you might want in that data set, and together select and project allows us to filter horizontally and vertically, and explicitly come back with the actual data that we want. Right. So these two allows us to center or on the subset of the data that we want. Sort allows us to just rearrange the original data set that comes back from a query and sort of ascending or descending on a particular field. Rename allows us to rename a particular field. These two, sort and rename, are mostly for presentation purposes, right? Where we might rename a field that might be an acronym or might be an abbreviation. We might expand it to something more readable. Or it's also useful if you have a table or a set that is joined on its own, on itself, right? Where you might have columns that have the same name, or you're putting together sets that might have properties that have exactly the same name, and it would be ambiguous, right, to know which one you're referring to. So rename allows you to deal with those issues. Extend is that you can add fields that were not in the original data set, right? Perhaps fields that can be calculated from two other data sets, right? Maybe you might want a field that says a full name, right? That was not in the original data set. You have first name, you have middle initial, and you have last name. But it would be redundant to have a field called full name, right? Because it is just a concatenation of all three different fields, right? It would be redundant to have an additional field. But you can calculate it on the fly, right? You can extend and add a new field on the fly when you query that says that this new field is a concatenation of three other fields, or is the summation of two other fields, right? Or some calculated value that is not worth storing, right? Because you can always retrieve it on the fly. GroupBy allows you to collate or aggregate various values into a single value, maybe to do summarize results that you might want to average out certain values. You might want to calculate the minimum, the maximum, or some aggregate value based on a set that are related to one another. Okay, so these are all considered to be operations on a single table, right? So you're given a particular table, and you can apply these operations on that one single table. Or you have operations that can deal with multiple tables, right? In this case, two at a time, right? And as we've seen in other courses that talk about binary trees and all sorts of n-ary trees, right? We see that we can always convert and represent any tertiary operation into multiple combinations of binary operations, right? So these binary operations that can deal with two tables at a time can be used to implement any n-ary operations, right, on multiple tables, right? So by being able to combine multiple of these operations, multiple of these two table operations to be able to operate on 3, 4, 5, or any number of tables. Make sense? So product allows you to calculate the product of two data sets, right? Which is basically calculating all the various possibilities of how you could possibly combine the data points on any two sets, right? So if you might have A, B, C on one set, and you might have 1, 2, 3 in another set, and what are all the possible combinations of A's with 1s, A's with 2s, A's with 3s, and then B's with 1s, and so on and so forth, right? And list all the various possible permutations that are combinations that you have between data points in two sets. Join allows you to do similar things, but allows you to filter and say, well, I might not want all possible combinations. I might want a subset of those. Some combinations might not make sense, right? Combining, for instance, students and the sections that they're in, right? Depending on the enrollment. Does it make sense to combine students with the sections that they're enrolled? Yeah, it makes sense, right? That you might want to know, given the students and given the sections that they're in, you can figure out that, okay, well, for these students, they are in this particular section, taught by this particular professor, right? And they got this particular grade. So it makes sense to group them together. But does it make sense to group students that with the sections that they're not enrolled in? Maybe not, right? Whereas product gives you all possible combinations. Some of those combinations just make no sense, right? Just relating students with sections that they're not enrolled in, yes? So join allows you to filter on all those possible combinations that might make no sense, right? Based on certain criteria, okay? Semi-joins and anti-joins. Semi-joins allow you to just match some of the fields and not necessarily bring them together. You might be interested in knowing which are the students that are enrolled in a particular section. You might not be interested in anything about the section itself, but you just might want to know about the students themselves, which ones are enrolled, right? But not actually retrieve the data from the data points from that second set, okay? Whereas anti-join, you might want to ask the inverse, which students are not enrolled in a section, right? So like maybe to, which are the ones that don't meet a particular criteria, right? Unions would allow you to group together data sets from data points from one data set and data points from a completely different data set, and as long as the properties match, right? For instance, I might want to join the list of all the faculty and the list of all the students, and just have a maybe a higher level collection of all people, right? Or all folks that are participants in the community of this university, right? Regardless of whether they're faculty, regardless of whether they are students. So I could unite, create the union between them, or I might be interested in the ones that are not part of this community, right? Which ones don't match, right? So these are various operations that are relational algebra has a very specific, very formal representation. So here's a two different syntheses for the same exact thing. So for instance, the functional syntax here, where we have Q1 is equal to select the student, comma, graduation year equal 2004. That's a more functional syntax, right? That says I want to calculate the select of this particular data set of students that meet this particular criteria, right? Where the graduation year is equal to 2004, right? This has a more formal syntax down below. Before, again, this is before we thought of what tables were and what rows were and columns and whatnot. This is a more formal representation of these, right? Sigma and then graduation year equal 2004, where you have the predicate graduation year equal 4 as a subscript, right? And then the applied to this particular table, right? So here's just a couple of these examples where you can also combine using Boolean algebra. You can combine various predicates where you can have I want to retrieve the data set or the data points in a particular data set of students that meet the following two criteria: the graduation year is 2004 and the major ID is 10. So everybody who's in computer science, right? And again, down below you have the equivalent in relational algebra. Okay. And you can certainly combine various other operations and, or, and whatnot. Okay. Again, this is not SQL, right? SQL is just one particular implementation, right, of relational algebra, right? And certainly, SQL did not go and implement everything in relational algebra, right? And relational algebra is so much more, right? It's a superset of SQL, right? Many of the operations that were originally envisioned, right, in relational algebra never actually were implemented in SQL, right? Relational algebra is so much more powerful and much more expressive than what the current implementation of SQL. Right. Certainly, SQL has gone quite far on going and trying to implement a lot of these ideas, but certainly not everything. Right. You can also nest queries where the results of one query, right, can be then used as an input for the following query, right? Where, for instance, here we have two queries where they were saying, I want the students who graduated in 2004 with a major of 10 or 20, meaning they either graduated in math or computer science. This is using the same database that we've been using from last week. So the inner one, we have that this one answers the first question of retrieving the graduate students in 2004. So this one, and then the result of that, right, can then be fed as a input for the outer one that uses a different criteria of major 10 or 2020. Or you can we're going to be using this syntax where the result of one of the queries can be assigned to a variable, which can then be used later on in subsequent queries, right? Just for reading purposes, right? It's easier to read. Okay. Or graphically, it's also useful to see how the data is flowing from the entire data set of students, right? And then it's filtered subsequently by several other queries. So the first query of selecting the graduation year 2004, and that feeds into the next one that filters it by major ID or 10 or 20. Okay. Project, as we mentioned earlier, right? So select filters horizontally. Vertically, right? Which rows, which data points meet our particular criteria. Whereas project, right, says I might not want all the fields, so I might want a subset of those fields or the columns, and so you can select which columns do you want. So given a particular a set of students where it contains the major that they're in, and certain other primary keys and whatnot. We might not be interested in that, so we might select and say that we're only interested in just a student name and when they're going to graduate. That's it, right? So more formally, right, we can say pi subname s name graduation year of that particular table, and you can certainly combine those two. You can combine them. First, retrieving the subset of data points that meet a criteria, and then once you have that, you can then filter out on the fields. You might only want the field student name, right? And again, graphically, you can do your student, filter only those records that meet the major ID, the predicate, and then filter out because you only want the student name, right? Graphically, or using relational algebra on the right-hand side, which is it's less verbose, right? They're certainly much less verbose and easier to read. Some queries you have to be careful that especially when they're nested, that the nested query is actually returning something that can be used by the outer query, right? It could be that the inner query doesn't return any data, right? And then they're mutually exclusive, and the inner query doesn't contain any of the data that could be used by the outer query. So for instance, here the first one is taking the entire data set of all the students, and it's filtering it and says, I don't want all the fields, I only want the student names, right? Well, this is completely useless to the outer query that wants to select by a predicate that is comparing the major ID. by the time we get to the outer query, we don't have the major ID anymore, right? We only have the student name, right? So this is a meaningless query since we don't have the inner query producing any data for the outer one. Okay. Sorting, again, this is mostly for for presentation purposes, right? As far as we're concerned, there is no need for there's no need to put the data points in any particular order, right? It only makes sense for us human beings if we want to see it in one particular order. Okay. Here we're asking to have a data set here, and that data set here is currently the entire collection of students, but it can certainly be a select statement, right? That filters on some subset of the data set, right? And then ask it to sort first by the first field and then by the second field. Again, mostly for just display purposes. Rename allows us to rename a field and just give it a different name that might be more useful, especially if you have data sets that might have properties that are the same, right? You might have two sets that have the same field name, maybe called name or title. Right? It's a very common name for a field, right? In different data sets, and you want to bring them together or unite them or join them, and the names would collide, right? So you can use rename to change those names so that they don't necessarily collide. Extend allows you to add brand new fields, right? Where you might want to on the fly calculate certain values as you are from a particular query. So here for instance, we are adding a new field and we call graduation class that calculates the difference between the current graduation year and the year that it was founded. Right. So this tells me, you are the 123rd class, right? Graduating class, right? So it calculates it on the fly. This is and gives it the name of this brand new column, right? And this column can then perhaps be used as a in a different query, right? This could be feeding into an outer query. GroupBy allows you to take a look at the values that are coming back from a query and see if they're equal. If they're equal, we would like to combine them, right, into classes that can then be aggregated, right? So, for instance, you might want to combine everyone who is in the computer science department, or somebody if they're in the math department, or right, and group them like that. And then what happens is that the original data, the actual data, right, you might have multiple records that meet a particular group, right? Say you want to group all the students that are in the College of Computer Science, right? Well, we might come back and say, oh well, there's 2,000 students that are grouped, right? Now, because they're grouped, the individual values for any one record is meaningless, right? Since you want to treat them as one single group, right? All the individual values of my grade versus your grade versus is meaningless, right? We are grouping it into a single value. We can only treat them as a collection of things, right? As an aggregate of those. We can calculate maybe who's oldest, right? Or who's making most money, right? Or who has taught a course most than everybody, right? But we can aggregate, right? We can calculate. We can return. We can answer things about the aggregate of all that all those records that met that particular collection or group or grouping. The syntax is that we group a table by the grouping fields, right? And all the fields need to be equal, right? And those that meet the criteria, we can then apply various aggregation functions on them. We can calculate the maximum, the minimum, the average, right, or the count, how many there are, right, and calculates a summary of that data that meets that criteria. So here's an example of grouping all the students by their major ID, and so there might be hundreds of students that are in a particular major ID, right? Maybe there are a couple hundred in major ID 10, another couple hundred in major ID 20, and so on and so forth. What could we say about each group? Well, we could calculate, the minimum graduation year, right? Or we can so we might calculate maybe a range of the graduation year, the minimum and the maximum. Right. So, for instance, here's an example of using GroupBy, right? Using the data set that we considered last week. We have Joey, Amy, Max, Sue, and so on and so forth here. Notice that each one is a different major ID. Right? Joe is in 10, Amy is in 20, Max is in 10 again, right? And we would like to be able to group them by major ID. That means that here are the ones that are in red, Joe, Max, and Lee, are now part of the same group. Yes? And so they're going to be collapsed into a single data set, right? Data point. So we lose, right, the original values that were there. We're going to forget the fact that Joe was in 2004 and Max was in 2005. The distinct values for each record are going to be lost when they're all going to be collapsed into a single value. We could aggregate and say and answer questions such as, what is the average graduation year? Right? We can add up all the graduation years and then divide by the count, and that gives me a single value that can aggregate that information. Or I can answer, what is the maximum graduation year, or what is the minimum graduation year? Those are all, valid questions that you can ask, right, about the collection of instances that are part of the same group. Make sense? Right? Same thing here. We have Amy, Sue, Kim, and Pat. They all belong to the group 20, right? And major ID 20, and so on and so forth. If we sort it by major ID, it might be a little bit easier to read. We have 3 that are in major ID 10. We have 4 that are in major ID 20, and 2 that are in major ID 30. Right? And then we can ask, what is the average graduation year by averaging out 2004, 2005, or we can ask the minimum, we can ask the maximum. Here we have in red asking what is the minimum, I believe. There we go. Right, so here we're grouping by student, by major ID, and we're asking what is the minimum graduation year and what is the maximum graduation year. So notice that these red, blue, and green map to these 3 answers over here, and that's how they've been calculated. Make sense? Right. So that's very important, right? To remember that none of the original data, right, makes it beyond this operation, right? So if this data then gets fed into other queries, okay, those other queries won't have access to any of the original data. Right? So you won't be able to ask specific questions about any particular student or any particular year, right? Since all they have been collapsed into a single value. Right? So that's very important to remember later on when we go to other topics. You can group not only by just one field, but you can group by multiple fields, right? Where we can combine different fields, maybe major ID and graduation year. And here, what we're saying that we're not just looking at the major IDs that are the same. I like to see which one both major ID and graduation year are the same, right? So if you take a look at over here, we have here we have 2 records that meet this criteria, right? Where not only is the major IDs the same, but also the graduation year are the same, right? So there's only 2 records that meet that criteria, right? That have the same major ID and the same graduation year, right? So these 2 records, 1 and 9, right, is one category, one group, and here's a second group that has major ID 10 and 2005. Obviously, there's no other records that meet that, right? So it's its own group, right? Here we have another one. We have where both the major IDs are the same and the years are the same, and so this is just one single group. And then we have two other groups, right? 2005 and 20, 2004 and 20. So we have three groups here, and we have another two groups here, and we have two groups here, and this is what we have here, right? We have for 10 and 2004, we have two groups. 10 and 2005, we have another group, and so on and so forth. Everybody okay? Right? And then we might want to ask, well, what can we calculate? Well, we can calculate, again, min, max, but we can also calculate the count. How many are there that are in computer science and are graduating in 2004, or in computer science but graduating in 2005? There's only one, right? Right, multiple groups. This is the same thing as we saw earlier. If you don't provide the fields that you want to group by, right? Group ID considers the entire data set as one single group, right? So if you don't say to group by major ID or year or whatever, right? It considers the entire data set, the entire data table as one large group, and you can ask questions about that entire data set. So for instance, you want to calculate what is the minimum graduation year in the entire student table, right? And it comes back as 2001. Right. If you don't provide the aggregation, it's just the resulting is the entire grouping field. Okay. You can also as you calculate and apply these aggregate functions, these aggregate functions have two versions, right? One, it considers values that have the same value as their own value. It will count them twice, right? If you have values that repeat, right, it will count them as individual ones. Whereas count distinct or sum distinct will make sure that if we already use a particular value, it will not use it again when it's aggregating those values. So, for instance, here we have grouping the students. Then you count the major ID, right? Right. It'll count the students only once for every single major ID, right? Which again might not make sense, right? For being able to answer that kind of question, you might want to count as it repeats the major IDs. As we said earlier in last week, null represents that we don't have a value, right, for a particular field, and it does not participate. It doesn't allow the records that have fields null don't participate in queries. We can't answer the question whether something is equal, something is less than, or greater than. So it does not participate in any of the predicates. Right. So careful when you are use specifically if you're using count, right? That some of the fields might be null, right? And so it might give you some answers, some counts that you weren't expecting. It says, wait a minute, I know there's more records in there. Why is it giving me such a low count, right? So to be safe, when you want to count per se, count on values on fields that you know are guaranteed to have an actual value that is not null, right? So for instance, on a primary key is a very common thing, right? To count on a primary key, since it's usually has a constraint that it cannot be null, and it's because it's being referenced by other fields. Here we are using several group IDs to answer questions. A couple of queries here. So, for instance, we want to answer which one, given these students enrolled in these particular sections and whatnot. I like to count how many A's have a particular section been given, right? And then across all sections, I like to know which section got the most A's, right? So for instance, what we might want to do is first from the enrollment table, right? That data set is where we are recording all those grades, all those letter grades, right? So first we're going to retrieve all the records from the enrollment table that tells us all the letter grades. That can then be fed, right? We can be grouped by the section ID, right? And then be able to count how many of those, are there, right? How many are there in the notice that we are using the primary key to count, making sure that it's not null, and that is going to group them and count them how many there are. So in the first one, this comes back with all the enrollments. These are all the enrollments where there has been a section that has given an A to a student, and these are the students 1, 4, and 6. Right? So we know exactly which students, but that's not the question. The question is not about the student. We want to know about the section. So here are the sections. 13 and 53 are the two sections that have given A's, and we like to be able to answer, well, which one has given most A's? Right? So we can group them by the section ID. So this will be its own group, whereas these two will be a completely different group, right? So we have here 53, and we're counting. All right, go away. We're counting. We're counting, saying that there's 2 A's in section 53, whereas there's 1 in section 13. Yes.
Now, when you go to pull this whole thing out, where it says instead of Q18, Q19, that would actually, it would be grouped by select and roll within the group by.
Oh, like nested?
Yeah.
Oh, yeah, definitely.
The whole thing.
Yes. Yeah, the whole thing expanded. Okay. Right. Yeah, this notation just makes it a little bit easier to present. Long queries. One, especially when one is nested inside of the other. But yes, you would nest them in there. Yes. Right. So this count here can then be grouped again by the count ID, right? And says, okay, well now consider this data set as one entire data set, right? Notice that we're not providing here a group by. We're not grouping by any particular field. So it considers the entire table as a single group, right? And then we can apply aggregate functions on the fields on that particular subset, okay? And then it calculates the aggregate function of telling me which one is the maximum.
So it doesn't tell you like which section that is, does it?
It doesn't tell you which section. You would need to go back and perhaps join these two together, right? And say that 2 is equal to 2. But that only works if no two sections have exactly the same number of A's. Right? And we'll come back to that question a little later to be able to answer those kinds of things. Which is this is one of the limitations of GroupBy. Okay, that you lose all the original data once you aggregate the functions, right? So you don't have access to any of the original data in the original data set, right? Because by the time you answer that question, all the data that was originally used is lost, right? So we would like to be able to use predicates while we are grouping, right? Which GroupBy just doesn't allow you to do that, right? Later on, when we see a couple other operations, we'll add.
Like a temporary table and then pull it out of there?
No. Well, we'll see how to handle that. So let's follow the query starting from the bottom and drawing what the query tree is. We start off with the enrollment table, and we filter out. We only want those records that have the grade A, and then we group by the section ID, counting how many enrollments there are, and that is fed into the next one that groups the entire data set and calculates the maximum in the enrollment. Okay. So up to this point, we've been using just single operation, single operations an operation on a single table, right? And so let's look at now operations that can operate on multiple tables, right? So for instance, we have two data sets, A and B. We would like to calculate the product. So product takes two original data sets and just combines them as they would all the various possibilities. So considering data sets A1 and A2, and then from a different data set B1 and B2, the cross multiplication just combines A1 with B1, A1 with B2, and then it goes on to next A2, B1, A2, B2, right? So this is kind of like a nested loop, right? You iterate over one of the data sets, and as you iterate over one, that you iterate over all the other data points in the other data set, right? So you first start with one A1, and then you iterate over the other ones, A1, B1, B2. Once you're done iterating over the second data set, you go on to the next in the previous data set, right? And then you iterate again, B1, B2. Make sense?
It's just matrix math.
Just matrix math, yes. But what I'd like to point out is that one way to calculate this is to use nested for loops, yes? And if you were combining three data sets, then it would be three nested for loops, right? So this points out the complexity of being able to calculate these products, right? That later on when we're going to consider joins, right? That you want to be able to look up and filter out using different predicates. Every time you add a new table to a predicate, right? You are in essence, right? Increasing the complexity, right? From linear to quadratic, to cubic. So it gets much more complex every time you're considering more of these tables that are participating in one of these, right? And that's later on going to be one of the reasons we're going to be considering. How do we optimize this? How can we optimize this so that we don't get into this complexity in exponential complexity, right? So we'll talk about that a little later when we talk about optimization, right? But it's based on this. It's based on that when you consider all the data sets, it just gets more and more. It gets exponentially hard, right? So here we have two tables. We have the student data set and we have the department data set. And I've color-coded it so you can follow along. Sorry for those who are colorblind. So we have here, let's just consider the first three records, right, of the left table, right? But certainly what we're going to look at would apply to the entire table. But here we're just going to consider the first three. Yes? All right? And so we want to do the product of students and department. So the way it would work is that for each one of these three, we need to consider all the combinations with the department, right? So we would have something like this, right? For the first three, these would all be combined with the computer science department. Obviously, this is only the first three, right? But certainly you have all 9 possible students in here combined with the computer science department. Yes? And then you would have again, it would repeat for the second data set, right? For the math department, and then again for the drama department, right? It would combine all possible combinations, right, of one data set with the other data set, right? Now, some of these combinations make absolutely no sense, right? Of combinations, for instance, over here we see that Joe here is in the major ID. It makes sense to that Joe has a relationship with the data that is on the other data set, yes? But what about this one? Amy is not in the major ID, right? Is not in the computer science department. Why is she even being considered with this combination? It makes no sense, right? Actually, most of these combinations are irrelevant, right? Should not even be considered, right? And that's why we're going to be looking a little later to joins, right? That filter out the ones that make no sense and only keep the ones that do make sense. Yes? All right. But before we get there, we're going to consider the cross product. right? So oftentimes we we don't want to consider all of them. We only want to consider the ones that make sense, right? Only the ones that meet a particular criteria. So here's product that calculates all possible combinations, and then we do a filter. Notice that this feeds into a select, right, of which we only want to keep the ones that make sense, where the major ID is equal to the department ID, right? So we only keep Joe, which is in the computer science department. We keep Amy, which is in the math, and we keep Max, which is in the drama department. Make sense? All the other ones are irrelevant, right? They don't make any sense. Now, this is such a useful operation, right? Of first calculating the product and then filtering on a particular predicate. It's so useful that it gets its own name, right? It's called the join operation, right? But never forget what's actually happening, right? It's first creating the product and then filtering, right? And so here we are joining. We're saying that we're going to join table T1 with table T2 on a particular predicate, right? And there's the formal representation in relational algebra, and this is a little more readable. Here we're joining student and department, where on the predicate major ID is equal to the department ID. Okay. So let's play around with the new join operation, right? Here we're first, and the answer that we want to, the question that we're going to answer here, we want to retrieve all the grades that Joe received in his courses during 2004. So first we can filter out all the records from the student table that has a student named Joe. Right? So we don't even want to consider any of the other students. Since it's this is looking at courses and grades, we know that the grades are captured inside of the enrollment table, right? So we need to we're going to join the records where Joe appears. We're going to join them with the enrollment. So this is going to create the cross product, right? And combine Joe with all the enrollments. Yes, of which we don't care about all of them. We only care about the subset where Joe, the SID for Joe, matches the student ID in the enrollment table. Right, so we are filtering out of all the possibilities of mixing Joe with the enrollment. We only want the ones that match Joe with the student ID in the enrollment table. So that gives us Q26. The other one is that since his courses, so that gives us the enrollments, right? The other one is that now why are we matching it with? Oh yeah, right. The year that it was offered, right? The year that was offered, that information lives on the section table, right? The section table tells what professor taught it, right? What year was it offered in that particular semester? Perhaps it has also semester information about spring, fall, summer 1, summer 2, right? Would be part also of that section table, right? And so we are retrieving only those sections that were offered in the year 2004, right? So we're not looking for all sections, and now we're going to join both together, right? The first the filtering of those sections that we found that Joe participates in together with those sections for that particular year, and joined in the field section ID equals section ID, right? And then we only care about the grade, right? So we're filtering here horizontally. We only care about the grade field for Joe, right? Graphically, we can render it this way, where we start off on the left-hand side, looking for all the records where Joe is in the student table, and then we join it with the enrollment table to extract those enrollments that has the section ID that tells us what section ID what this Joe participated in the student table. We then retrieve the sections from the section table on the right-hand side, and both of these contain the section ID, which we can then join above and filter. Only those cross products for the section ID are the same, and we extract only the grade information. Make sense? Okay. Oh, this might be my guest. Hello? All right, I'm gonna come and get you. Yes, I'll be right there. Hold on. Okay, let me stop this for a second.